Greetings of the day to all of you. I welcome you all to last lecture of module number 3. In today's lecture, I am not going to discuss something new. I am going to give a summary of what we have learned in module 3. Our module 3 was mostly, in module 3 we mostly, in module 3 we mostly discussed about sine triangle modulation or triangle comparison. Initially we discussed single phase PWM voltage source inverters with bipolar PWM and unipolar PWM techniques, and then bus clamping was also discussed in single phase PWM voltage source inverters. Then we discussed three phase PWM voltage source inverter with sine triangle modulation, and then we discussed third harmonic injection PWM technique. We then discussed discontinuous PWM technique, in which we discussed various bus clamping PWM techniques like 60-degree clamp PWM techniques and split clamp PWM techniques. Let us summarize what we have learned over the last few lectures in module number 3. So I will write here a summary of triangle comparison, triangle comparison based PWM, or this is also called carrier based PWM, carrier based PWM techniques. Okay, actually why is it called triangle comparison based PWM technique? Because you have modulating reference waves, which may be sinusoidal modulating waves or which may be non-sinusoidal modulating waves. You are comparing those modulating waves with a common high frequency triangular carrier wave. So since the modulating waves are compared with high frequency triangular carrier wave, that's why these types of PWM techniques are also called triangle comparison based PWM techniques. They are also called carrier based PWM techniques because the reference waves or the modulating waves have to be compared with high frequency triangular carrier. This high frequency wave, which determines the switching frequency of your inverter, this is also called carrier wave. So triangle, this carrier comparison is always there. Modulating waves have to be always compared with the triangular carrier. That's why these techniques are also called carrier based PWM techniques. Now we already know that the modulating signals are all compared with high frequency triangular carrier. That's the fundamental of triangle comparison based PWM techniques or carrier based PWM techniques. What we do here, modulating waves. Now when I say modulating waves, they may be sinusoidal or non-sinusoidal. Sinusoidal or non-sinusoidal. So modulating waves are compared with high frequency triangular carrier wave, which is common triangular carrier wave. The frequency of modulating wave will determine the frequency of inverter output voltage. That's the fundamental frequency. And the frequency of triangular carrier wave will determine the switching frequency of various IGBT switches of the inverter. Now, when I say modulating waves, our modulating waves may be sinusoidal like this, as we have already discussed. These may be our modulating waves, MR, MY, MB, or they may be non-sinusoidal like this, like in third harmonic injection PWM technique, we had modulating waves something like this, non-sinusoidal. Okay. So if common mode injection is not done, then our modulating waves will be purely sinusoidal waves. And if we go for common mode injection, like third harmonic injection PWM technique or discontinuous PWM techniques like bus clamping PWM techniques, in these techniques we are going for common mode signal injection. So if common mode injection is done, then our modulating signals get modified and they become non-sinusoidal modulating signals. And we know that the simple, how do we generate the control pulses. We have modulating wave like this. This may be modulating wave, say MR star. It is compared with high frequency triangular carrier wave. And logic is simple. Whenever the amplitude of modulating wave is higher than triangular carrier wave, top switch of a particular inverter leg is on. Okay, and whenever triangular carrier wave is higher in amplitude than modulating wave, the bottom switch of same phase leg is on. We have been discussing this technique, this method of generating the gating pulses over last many lectures. Okay, now let me discuss with you average voltages for sinusoidal modulating waves. Sinusoidal modulating waves. Now, when I say average voltages, it means instantaneous average pole voltages, instantaneous average line voltages, and instantaneous average phase voltages. Okay. Now, our modulating waves, if our modulating waves are sinusoidal, they are given as, I will write here, modulating waves are. We have three modulating waves, MR, which causes the switching of phase leg R. It is given by Vm sine omega t. We have another modulating wave, My, which causes the switching of phase leg Y, and this is given by Vm sine of omega t minus 120 degrees. Okay, and we have another modulating wave, Mb, which causes the switching of third phase leg, that's phase leg B. It is Vm sine of omega t minus 240 degrees or omega t plus 120 degrees. Okay, these are all sinusoidal modulating waves. Sinusoidal modulating, they are also called target reference waves. Target reference, you call them modulating waves or target reference waves. They are sinusoidal and their peak value is Vm. The peak value depends upon the modulation index. Okay, if modulation index is less than 1, then this Vm will be less than 1. It will be less than Vp, where Vp is the peak of the carrier. This is minus Vp and this is plus Vp. Okay, it may be, Vm may be less than Vp, or it may be equal to Vp, or it may be greater than Vp. It will be less than or equal to Vp for under modulation mode of PWM technique, and it will be greater than Vp if we go for over modulation. We already know this. Okay. Now, since these are our three target reference waves, sinusoidal target reference waves or sinusoidal modulating waves, let me write the mathematical expressions for instantaneous average pole voltages. Instantaneous average pole voltages. Now we know our pole voltages are something like this. These are our pole voltages, say positive half cycle, and then similarly for negative half cycle like this. Okay, our pole voltages go from plus VDC by 2 to minus VDC by 2. Then again from minus VDC by 2 to plus VDC by 2. Now if you, in half carrier, if you find the average pole voltage, in half carrier, you are, in half carrier wave, this is full carrier wave and this is half carrier wave. You will have pole voltage like this, plus VDC by 2 and minus VDC by 2. I mean, you will get one voltage pulse like this. Find its average value. Then find average value in next half carrier. Then find average value in next carrier. See, this is one carrier, another carrier, another carrier. There may be hundreds of carriers. So in positive half cycle of inverter output voltage, from one carrier cycle to another carrier cycle, you keep on finding instantaneous average pole voltage. Like for example, you find the instantaneous average pole voltage of this. It may be somewhere here. Find the instantaneous average pole voltage of this here. Find the instantaneous average pole voltage of next voltage pulse. So keep on finding. So you will get something like this. So for sinusoidal reference waves, sinusoidal modulating waves, the instantaneous average pole voltages will vary like this. They will also increase from one carrier cycle to another carrier cycle in a sinusoidal manner. I mean, they will also vary from one carrier cycle to another carrier cycle in a sinusoidal manner, and they will give something like this. If you join these values, you'll get something like this. This may be pole voltage VRO. Similarly, your VYO will also be sinusoidal, and instantaneous average pole voltage VBO will also be sinusoidal like this. Okay, so therefore, if you are modulating waves or target reference waves are sinusoidal, instantaneous average pole voltages will also vary sinusoidally in DC to AC converters, that is in inverters. Whereas in DC to DC converters, which you must have studied in your BTech Power Electronics, the converter output voltage is like this. If you find average of first voltage pulse, take first voltage pulse on period and off period, find its average value. It will have some average value, say this. Then find average value of second pulse, it will be same. Find average value of third, it will be same. So if you find the average value of different voltage pulses, you will get something like this, you will get constant. So that means in DC to DC converters, the instantaneous average value of various voltage pulses, okay, from one carrier cycle to another carrier cycle, it will be constant. That is not the case in DC to AC converters or inverters. In inverters, the instantaneous average value of pole voltages from one carrier cycle to another carrier cycle over one full cycle of inverter output voltage, the instantaneous average pole voltages will vary sinusoidally like this. Okay. In DC to DC converters, I repeat, the instantaneous average value of pole voltages will remain constant like this, okay, for a given duty ratio. But for voltage source inverters, DC to AC converters, the instantaneous average pole voltages will vary sinusoidally like this. Okay, so therefore, if you find mathematical expressions for these instantaneous average pole voltages, so pole voltage VRO average, so average value of instantaneous average value of pole voltage VRO, so it will be, we already know, I have already discussed with you, it is V control by VTRI into VDC by 2. I have discussed it when we were discussing bipolar PWM technique of single phase PWM voltage source inverters. Okay, well, what is this V control? V control is capital V control, is the peak of reference. V control is the target wave or modulating wave, sine omega t. And what is this V control? We can also write as MR, because just few moments back we have written three modulating waves. We have not represented them, we have not denoted them by V control, we have denoted them by MR, MY and MB. So this MR can be written as peak values V control. So instead of writing V control, I can write VM, sine omega t. Similarly, MY is VM sine of omega t minus 120 degrees, and MB is VM sine of omega t plus 120 degrees, right? So therefore, and what is peak value of triangular carrier wave? That is VP. So this is your triangular carrier wave, its peak value is VP. So here I have written VTRI. So you can write VTRI also, or you can write VP. So let us follow this notation. Instead of writing V control and VTRI, we will write MR, MY, MB and VP. So therefore, instantaneous average value of pole voltage VRO will be equal to, what is this V control? V control is MR, modulating wave, divided by VTRI. It's the peak of triangular carrier wave, and it is VP. So MR by VP into VDC by 2. And we already know what is MR. MR is VM sine omega t. So it is VM by VP into VDC by 2. Then I can write sine omega t here. So it is a sinusoidal modulating wave. Okay. So this is my pole voltage MR, and it varies sinusoidally. Similarly, instantaneous average value of pole voltage VYO average will be equal to My, the modulating wave or target reference wave of for phase leg B, which gives pole voltage VYO, is My. So My by Vp, where Vp is the peak of triangular carrier wave, into Vdc by 2. And for phase B, so for third phase leg B, the pole instantaneous average pole voltage VBO average will be equal to MB. MB is its modulating wave or target reference wave. So MB by Vp into Vdc by 2. Right? So therefore, it's we can say that these pole voltages vary sinusoidally, because, for example, if you write mathematical expression for instantaneous average pole voltage VRO, it is Mr by Vp Vdc by 2, and Mr we know is Vm sin omega t. So it is Vm by Vp Vdc by 2 sin omega t. And by the way, what is this Vm by Vp? It is modulation index. So it is Ma Vdc by 2 sin omega t. This is very well known equation we have already discussed in single phase PWM voltage source inverters. So that means all the three pole voltages, they vary sinusoidally, as you can see. And very interestingly, you can see if you take again instantaneous average value of pole voltage VRO, it is Mr by Vp Vdc by 2. Okay, so you can see it is, or you can say it is Vdc by 2 Vp into Mr. I have told you in many classes previously that whatever is the pattern of your modulating wave or target reference wave, same will be the nature of pole voltages. And that is proved by mathematically also here, because your instantaneous average pole voltage VRO average is equal to, I can write again, Vdc by 2 Vp into Mr. So it is directly proportional to Mr. In fact, I would like to say that it is the amplified version of modulating wave. What is this? This is gain of inverter. Gain of inverter. Because just few moments back I told you that if this is your Mr, modulating wave Mr, your pole voltage will also be sinusoidal. Pole voltage VRO, average instantaneous average values will also follow sinusoidal pattern. It will follow same pattern as Mr. But VRO will not be equal to Mr. It will be, Mr into gain of the inverters. What is Vdc by 2 Vp? It is the gain of inverter. Okay, so therefore we can say that the pole voltages are scaled versions of modulating waves. And since your modulating waves are sinusoidally varying, the instantaneous average pole voltages VRO, VYO and VBO, they also vary sinusoidally. Okay, that is about instantaneous average pole voltages. What about instantaneous average line voltages? So I will write now instantaneous average line voltages. Let me take one line voltage. Say VRY, line voltage VRY is instantaneous average values. So it is equal to, we already know it is VRO average minus VYO average. So line voltage VRY is pole voltage VRO minus pole voltage VYO. And VRY average is equal to, what is VRO? Just few moments back we have written VRO average is Mr by Vp into Vdc by 2 minus what is VYO? This is My by Vp Vdc by 2. Okay, so line voltage VRY average is equal to, I can take Mr by 2 Vp common, so Mr by 2 Vp Vdc by 2 Vp I can take common in both the terms. So Vdc by 2 Vp, what I get inside is Mr minus My. So this is instantaneous average value of line voltage VRY. So you can see it is Vdc by 2 Vp to Mr minus My. So since Mr modulating wave is sinusoidally varying, My modulating wave is also sinusoidally varying, that means our line voltage is also sinusoidal in nature. So it is sinusoidal in nature. Similarly, the other line voltage, instead of writing line voltage, I will write line voltages. Other line voltages VYB average is equal to, on the same pattern, we can write VDC by 2Vp into My minus Mb. Okay, and the third line voltage, VBR, instantaneous average value of line voltage VBR, is equal to VDC by 2Vp into Mb minus Mr. So these are three line-to-line voltages, and they are all sinusoidally varying because they are scaled versions of difference of these modulating waves. Like VRY is scaled version of Mr minus My. Since Mr is sinusoidal, My is also sinusoidal, so their difference is also sinusoidal. VYB is scaled version of My minus Mb. VBR is scaled version of Mb minus Mr. So since our pole voltages are modulating waves are sinusoidally varying, our line voltages will also be varying sinusoidally. Fine. This was about line voltages. What about phase voltages? Let us take one phase voltage. I will write here instantaneous average phase voltages. Phase voltages. We can take one phase voltage like VRN average, this instantaneous average value of phase voltage. For example, your load may be like this. Okay, and this is the neutral of the load. So voltage of phase R with respect to neutral. So this is your phase voltage VRN. So this VRN mathematically it is given by, you should remember, it is given by VRY average minus VBR average by 3. This is the mathematical expression for phase voltage. We must have discussed it somewhere in 6-step voltage source inverters. Okay, now phase voltage, instantaneous average value of phase voltage VRN is equal to, what is VRY? It's the VRY average, it is the average value of line voltage. Just few moments back, this VRY average was written, it was derived as, it is equal to VDC by 2Vp into Mr minus My. Minus, what is VBR? It's also a line voltage, and just few moments back it was proved that it is equal to VDC by 2Vp into Mb minus Mr. This whole thing divided by 3. Okay, this is divided by 3. So if you open it, it will be VDC by 2Vp. Take VDC by, okay, let's first expand it, Mr minus My minus VDC by 2Vp Mb minus Mr, whole divided by 3. So I have rewritten it. So I will take VDC by 2Vp common. So this is VDC by 2Vp. What I get inside is Mr minus My minus Mb, minus into minus is plus Mr. This whole thing divided by 3. Okay, so therefore VRN average, I will again write, it is equal to, what is it equal to? Just few moments back I have written, it is VDC by 2Vp into it is Mr minus My minus Mb plus Mr, this whole thing divided by 3, or this can be written as VDC by 2Vp, this 1 by 3 I can write here, into, what is Mr plus Mr? This is 2Mr minus My minus Mb. Now we know that since our modulating waves are balanced modulating waves, their sum is 0. They are sinusoidal 120-degree displaced modulating waves, balanced modulating waves. So Mr plus My plus Mb is equal to 0. Okay. So from this, what is Mr? Mr is equal to minus My minus Mb. So therefore minus My minus Mb is equal to Mr substituted here. Therefore instantaneous average phase voltage Vrn is equal to Vdc by 2Vp into 1 by 3 into 2Mr minus My minus Mb, and minus My minus Mb is equal to Mr. So that is equal to Vdc by 2Vp into 1 by 3 into 2 plus 1 is 3. So this is 3 Mr. So this 3 and 3 goes. So that gives instantaneous average phase voltage Vrn equal to Vdc by 2Vp into Mr. So that can also be written as Mr by Vp into Vdc by 2. And what is this equal to? What is Mr by Vp Vdc by 2? It is same as pole voltage VRO, average pole voltage VRO. Because just few moments back we have written average pole voltage VRO equal to Mr by Vp Vdc by 2. This phase voltage Vrn, average phase voltage Vrn also comes out to be same. So therefore phase voltage average phase voltage Vrn will be same as average pole voltage VRO. Similarly, I will write similarly Vbn average will be equal to VBO average. Now of course that will be Mb by Vp into Vdc by 2, and Vyn average will be equal to My by Vp Vdc by 2, that will be equal to Vyo average. So therefore phase voltages are same as pole voltages, and since your pole voltages are sinusoidal, your phase voltages will also be sinusoidal in nature. So we have therefore found the instantaneous average voltages, instantaneous average pole voltages, instantaneous average line voltages, and instantaneous average phase voltages for a three-phase PWM voltage source inverter, assuming that it is modulated by sinusoidal target reference waves, or it is modulated by sinusoidal modulating waves Mr, My, Mb, and we have proved that since the modulating waves or target reference waves are sinusoidal, the pole voltages, the line voltages, as well as the phase voltages are also sinusoidal in nature. Okay. In fact, the line voltages are line voltages or pole voltages are scaled versions of modulating waves. Okay. So that was about if modulating waves are purely sinusoidal in nature. What if modulating waves are not sinusoidal in nature? I mean, if we go for common mode injection, because in common mode injection our modulating waves or target reference waves, they get modified and they no longer remain sinusoidal. Okay, so now I am going to discuss with you instantaneous average voltages of a three-phase PWM VSI voltage source inverter with common mode injection. Few moments back we discussed instantaneous average voltages of three-phase PWM VSI with sinusoidal modulating waves or sinusoidal target reference waves. Now we are having common mode injection. A common mode signal MCM is added to all the three phases and it modifies the modulating waves. So with common mode injection, our target reference waves or modulating waves, they are no longer sinusoidal, they are distorted, they are non-sinusoidal. And what will be the instantaneous average voltages if we do the common mode injection? When I say common mode injection, it will be third harmonic injection PWM. It will give third harmonic injection PWM technique, or it will give discontinuous PWM technique. Discontinuous PWM techniques, and discontinuous PWM techniques are also called bus clamping PWM techniques. Bus clamping PWM techniques. So whenever common mode injection is done, either we will get third harmonic injection PWM technique, or we will get discontinuous or bus clamping PWM techniques. Okay, so again we will write that original modulating or target reference waves are, let me write them again, MR is equal to Vm sine omega t. Similarly, My is equal to Vm sine of omega t minus 120 degrees, and Mb is equal to Vm sine of omega t plus 120 degrees. Now what we are doing, we are adding common mode signal to all the three original target reference waves or original modulating waves. So with the addition of a common mode signal, which may be a third harmonic wave or any other wave, with the injection of a common mode signal or common mode voltage MCM, okay, with the injection of a common mode signal MCM, the target reference waves, the target reference or modulating waves are modified as follows. How are they modified? Your R phase modulating wave, original modulating wave is Vm sin omega t. When I am adding common mode voltage to it, so it gets modified to Mr star. So Mr star will be equal to original sinusoidal modulating wave or original sinusoidal target reference wave to common mode voltage MCM. Similarly, My star will be equal to My original target reference wave plus common mode voltage MCM. Similarly, Mb star will be equal to original modulating wave Mb plus common mode signal or common mode voltage MCM. Okay. So now these are our target reference waves. Our target reference waves are not Mr, My, Mb. They are no longer sinusoidal. They are now non-sinusoidal. Our target reference waves or modulating waves are Mr star, My star, Mb star. Let us see how they affect the average pole voltages, average line voltages, and average phase voltages. So I will now write average pole voltages. So let me find mathematical expression for instantaneous average pole voltages. So my first pole voltage is VRO average, instantaneous average pole voltage. So it will be now Mr star by Vp into VDC by 2. When our modulating signal was sinusoidal, I had written Mr by Vp VDC by 2. Now it has got modified from Mr to Mr star. So therefore VRO average will be Mr star by Vp VDC by 2. And since your Mr star is, what is your Mr star? Mr star is original sinusoidal modulating wave or original sinusoidal target reference wave plus common mode voltage. So it is non-sinusoidal. Since your target reference wave, modified target reference wave or modified modulating wave is non-sinusoidal, so your pole voltage VRO average value will also be non-sinusoidal. For example, let us suppose this is our target reference wave. So this is our Mr star. So what will be pole voltage VRO? Our pole voltage VRO will exactly follow the same pattern. Its instantaneous average value will be same. You can see our instantaneous, average pole voltage VRO is equal to, VDC by 2 Vp into Mr star. So it is equal to Mr star into gain of inverter. This is gain of inverter. So that means the instantaneous average pole voltage VRO is the scaled version of this modulating wave. And since your modulating wave is like this, your instantaneous average pole voltage VRO will also follow the same pattern. So it will also be same. And what is it? It is equal to VDC by 2 VP into MR star. So it is the scaled version of MR star. It will exactly follow the same pattern. Okay. So this is MRO. Same will be case with VYO and VBO. So I can write that instantaneous average value of instantaneous average pole voltage VYO average will be equal to MY star by VP into VDC by 2. Here it is MR star by VP VDC by 2. Here it will be MY star by VP VDC by 2. And instantaneous average pole voltage VBO will be MB star by VP into VDC by 2. So therefore, instantaneous average pole voltages, that is VRO average, VYO average and VBO average, are scaled versions of modified modulating waves or modified target reference waves, or scaled versions of modified modulating waves, modified modulating waves, MR star, MY star and MB star. That's very important. So therefore our pole voltages will no longer be sinusoidal, because our modulating modified modulating waves have got distorted. Pole voltages will also get distorted. They are basically scaled versions of modulating waves. And since modulating waves are no longer sinusoidal, instantaneous average pole voltages will also no longer be sinusoidal. They will be having same shape as the modified modulating waves. Fine. That is about pole voltages. What about line voltages? So instantaneous average line voltages. Let us now see mathematically how these line voltages look like. So let us take VRY average, instantaneous average value of line voltage VRY. Okay, so it is equal to instantaneous average pole voltage VRO minus instantaneous average pole voltage VYO. So VRY is VRO minus VYO, right? And what is instantaneous average pole voltage VRO? Just few moments back we have written it is MR star by VP into VDC by 2 minus what is VYO average? It is MY star by VP into VDC by 2. Fine. So if I take VDC by 2 VP common, what I get inside? I get inside MR star minus MY star. Now I already know MR star is the modified target reference wave or modified modulating wave. It is basically MR plus MCM. And I also know MY star, that is the modified modulating wave. MY star is original modulating wave MY plus common mode signal MCM. So I can substitute it here. So therefore I will get VDC by 2 VP to MR star. MR star is MR plus MCM minus MY star. It is also MY plus MCM. So MY minus MCM. Now as far as this common mode signal is concerned, it will subtract from line voltage, in the line voltage, MCM minus MCM. Subtract to 0, they cancel out. So therefore, line voltage VR by average is equal to VDC by 2 VP into MR minus MY. So it is not VDC by 2 VP, MR star minus MY star. MR star I substitute MR plus MCM, MY star I substitute MY plus MCM, MCM and MCM cancel. So that means the common mode signal subtracts from line voltage. It cancels in the line. It does not appear in the line voltage. Therefore, although my modified modulating waves are non-sinusoidal, which makes pole voltage is also non-sinusoidal. but my line voltages are sinusoidal. Since MR is Vm sin omega t and My is Vm sin of omega t minus 120 degrees, both are original modulating waves. They are sinusoidal. So my line voltage VR by average is also sinusoidal in nature. Similarly, what will be V by B average? That will be VDC by 2Vp into My minus Mb. And the line voltage VBR average will be equal to VDC by 2Vp into Mb minus Mr. So they are sinusoidal. So that means all the common mode, when common mode injection is done, your target reference waves or modulating waves, they get distorted, they become non-sinusoidal, which makes pole voltage also distorted, but line voltages still remain sinusoidal. Line voltage, because these common mode signals do not appear in the line voltages, they cancel to zero. Okay, so our line voltages still remain sinusoidal. Since our line voltages are sinusoidal, what about phase voltages? Let us take instantaneous phase voltages, instantaneous average phase voltages. Instantaneous average phase voltages. Let us take instantaneous average phase voltage VRN average. Just few moments back we have written it. It is equal to VRY average minus VBR average by 3. So that is equal to, what is VRY average? This is my VRY average. So I will substitute it here. The VDC by 2Vp into Mr minus My minus VBR average. This is my VBR average. It is also VDC by 2Vp into Mb minus Mr. Mb minus Mr. This whole thing divided by 3. Okay. So that will be equal to, let me take VDC by 2Vp and 1 by 3 common. So inside I will get Mr minus My minus Mb, minus into minus is plus Mr. Okay, so that will be equal to VDC by 2Vp into 1 by 3. Mr plus Mr is 2Mr. And what is minus My minus Mb? See, we know Mr plus My plus Mb is equal to 0. That makes Mr equal to minus My minus Mb. So minus My minus Mb is Mr. So this will again substitute. This is equal to Mr. So therefore, this is equal to VDC by 2Vp into 1 by 3 into 2Mr plus Mr is 3Mr. So 3 and 3 cancels. That means instantaneous average phase voltage, VRN average, is equal to VDC by 2Vp into Mr. That is equal to Mr by Vp into VDC by 2. So isn't it equal? So it is not equal to pole voltage VRO average, because with modified target reference wave, what was our average instantaneous average pole voltage? That was Mr star by Vp into VDC by 2. That was not Mr by Vp VDC by 2. That was Mr star by Vp VDC by 2. But our instantaneous average phase voltage VRN, it is Mr by Vp VDC by 2. It is not Mr star by Vp VDC by 2. So therefore, instantaneous average phase voltage VRN is not equal to instantaneous average pole voltage VRO. And since instantaneous average pole voltage VRO was non-sinusoidal because of target reference wave, modified modulating wave, our instantaneous average phase voltage VRN is sinusoidal because it is not given by Mr star by Vp, it is given by Mr by Vp, original modulating wave. And since our original modulating wave is sinusoidal, so that means instantaneous average pole voltage is also sinusoidal in nature. So that means distortion of modulating waves does not cause distortion in line voltages and in phase voltages. So in a similar way, we can write Vyn average equal to My by Vp VDC by 2. And similarly, we can write VBN phase voltage average. phase voltage VBN average equal to MB by VP into VDC by 2. This is very important. So that makes it clear that although with the injection of common mode signal MCM in all the three original modulating waves, the modulating waves got modified to MR star, MY star, MB star. They no longer remain sinusoidal, and our pole voltages also are scaled versions of modified modulating waves. Pole voltages, instantaneous average pole voltages are also not sinusoidal, but that does not affect inverter output voltages as line voltages and phase voltages. Our line voltages and phase voltages are in terms of original modulating waves, not in terms of modified modulating waves. And since original modulating waves are sinusoidal, our line voltages and phase voltages also are sinusoidal. In other words, this common mode signal does not appear in either line voltages or phase voltages. So inverter output voltage, average inverter output voltage remains sinusoidal. Now, as far as this common mode injection is concerned, we already know that we have discussed this common mode injection in details in last 3 to 4 lectures. The first method which was discussed was third harmonic injection PWM. Third harmonic injection PWM technique. This is the first type of PWM technique in which common mode injection is done. And here with common mode injection, our MR star becomes MR plus MCM, where MCM is the common mode voltage. MY star becomes MY plus MCM, and MB star becomes MB plus MCM. So we can write these modified target reference waves or modified modulating waves, MR star, MY star and MB star like this. Let us write first of all MR star. MR star is original modulating wave, which is Vm sine omega t, and with third harmonic injection PWM, common mode signal is KVM sine 3 omega t. The frequency of third harmonic wave is 3 times the fundamental frequency. That's why I have written sine 3 omega t. And its amplitude is not Vm, it's a fraction of Vm, k times Vm. Similarly, the modified modulating wave My star is My plus MCM. My is Vm sine of omega t minus 120 degrees plus MCM is common mode voltage, third harmonic voltage, KVM sine 3 omega t. And MB star is MB plus MCM. MB is Vm sine of omega t plus 120 degrees plus MCM remains say KVM sine 3 omega t. And some very important conclusions were made. One of the conclusions or one of the summary was that peak value of modified modulating wave or modified target reference wave, peak value of modified modulating wave is less than that of sine wave. Okay, so for example, if this is your sine wave, original modulating wave MR, your target reference wave or modified modulating wave is something like this with third harmonic injection. So this is MR star. And if you remember, we have observed that if this is the peak of this is the peak of original modulating wave, Vm. This is the peak of modified modulating wave. Okay, it is always less than Vm. It cannot be equal to Vm or it cannot be greater than Vm. It's always less than Vm. Remember this. We have already noted this. That was first point. The second point was that Vm is greater than Vp without pulse dropping. Without pulse dropping. See, if third harmonic injection is not done, then I have told you that in order to get higher inverter output voltage, we have to go for overmodulation. This is overmodulation. So So for example, this is 1, this is minus 1, I mean this is Vp equal to 1, and this is minus Vp equal to minus 1. The modulating wave Mr is greater than this. And when sine triangle, this is done, I mean comparison is done, then we find that there is pulse dropping from this instant to this instant. Our pole voltage becomes flat near the peak. Same is the case with line voltages, they also become flat because there is pulse dropping over this period when over which overmodulation takes place. But with third harmonic injection PWM, our target reference wave, modified reference wave, it is not going above 1.0, its peak is 1.0, not more than that. And when this is done, I mean sine triangle, when this triangle comparison is done, then no pulse dropping is there. There is no pulse dropping. The pole voltage is like this. I mean there is no pulse dropping. So therefore inverter output voltage, I mean if you see the pole voltage, that will be non-sinusoidal, but line voltage will be sinusoidal. The phase voltage, instantaneous average value, will also be sinusoidal. There is no pulse dropping, so no flat peaks. The peaks will be sinusoidally varying in case of line voltage as well as in case of phase voltages. So therefore actually we are making Vm greater than Vp. That is, original modulating wave goes greater than Vp. It's in over-modulating mode. But the modified target reference wave, that's its peak is equal to Vp. It's not greater than Vp. So there is no pulse dropping taking place at all. Another point we found is that for k equal to 1 by 6 gives higher or highest inverter AC output voltage. Okay, the optimum value, if optimum value of k is 1 by 6, it gives highest inverter AC output voltage. That means inverter AC output voltage increases by 15.5% higher. Just 15.5% higher. It increases the inverter output voltage by about 15.5%. And on the other hand, for k equal to 1 by 4, if k is 1 by 4, this is the optimum value of, it gives best or it gives lowest harmonic distortion. It gives lowest harmonic distortion. K equal to 1 by 6 will give highest inverter output voltage, which that means it will increase inverter output voltage by about 15.5%, but k equal to 1 by 4 will give lowest harmonic distortion. That is the best harmonic spectrum of inverter output voltage. It also increases inverter output voltage, but not by 15.5%, less than that, about 12%. But it gives best harmonic spectrum, or it gives lowest harmonic distortion. And finally, last point is that minus Vp less than or equal to Mr star less than or equal to Vp. The Mr star, I have already told you, this is your Mr star. For example, if this is your Mr star, its peak value is either Vp, positive peak, and negative peak is minus Vp, but it's never greater than Vp. It's not in overmodulation. It's either less than Vp or equal to Vp. Similarly, it is equal to minus Vp in the negative half cycle, or less than minus Vp. So this is the range of Mr star. Similarly, My star and Mb star also. So that was about third harmonic injection PWM technique. Some of the points which we have already discussed. This is the summary of all that. And then after this, a summary of continuous and discontinuous PWM techniques. Continuous and discontinuous PWM techniques. We have already discussed. We know that modulating wave can be continuous. I will write here target reference wave or modulating wave can be a continuous function of time or discontinuous function of time. Can be a continuous or discontinuous function of time, thus giving continuous or discontinuous PWM. Continuous or discontinuous PWM technique. Which of the PWM techniques are continuous and which are discontinuous? You know, I have already discussed with you sine triangle modulation. And if your modulating waves are sinusoidal like this, and they are compared with triangular carrier like your bipolar PWM technique, unipolar PWM technique, and three-phase PWM voltage source inverter where the three modulating waves are sinusoidal, that gives sine triangle modulation. So sine triangle modulation and third harmonic injection PWM and third harmonic injection PWM techniques, they are the examples of continuous PWM techniques or continuous PWM techniques. I have already discussed with you because the modulating waves in both the cases are continuous functions of time. These are the modulating waves in case of sine triangle modulation, MR, MY and MB. This is MR, MY, MB. They are continuous functions of time. You can see continuous function of time, continuous function of time. So therefore sine triangle modulation, it's a continuous PWM technique. Similarly, third harmonic injection PWM like this. This is MR star, for example. This is MY star, and this is this is MB star. These modulating reference waves, you can see they are also continuous functions of time. They are also continuous functions of time. So therefore, third harmonic injection PWM technique is also an example of continuous PWM technique. So sine triangle PWM technique and third harmonic injection PWM technique, they are the examples of continuous PWM technique. What are the examples of discontinuous PWM technique? All bus clamping techniques are examples of discontinuous PWM techniques. I will write here next point. Bus clamping PWM techniques. Bus clamping PWM techniques are discontinuous PWM techniques. They are all discontinuous PWM techniques. Because in all of them, the modified modulating waves, they are discontinuous functions of time. For example, this may be modified modulating wave. We have already discussed it in three-phase PWM voltage source inverter. Your modulating wave is like this. It is sinusoidally varying. I mean, it's a continuous function of time here. Then there is a jump. And jump means it becomes discontinuous here. Then there is a jump here also. So it becomes discontinuous function of time. There is a jump here. It becomes again discontinuous function of time. There is a jump here. There is a jump here. There is a jump here. So this modified modulating wave, it may be MR star for bus clamping technique. It is a discontinuous function of time. And therefore, all bus clamping PWM techniques are the examples of discontinuous PWM techniques. They are all discontinuous PWM techniques. So one point you have to write here that clamping of each phase leg or clamping of each phase to a DC bus takes place over certain intervals of time or over certain intervals in a line cycle. Okay, for example, let us consider this type of PWM. In this case, the phase leg R phase is clamped to positive DC bus for 60 degrees. Okay, over this period of time. This may be, for example, 60 to 120 degrees. And in the negative half cycle of this line cycle, this is line cycle, your phase leg R phase gets clamped to negative DC bus. for again over a period of time, say from 300 degrees to 270 degrees to 330 degrees. Okay, it gets clamped to negative DC bus like this. Okay, so phase R is clamped to positive DC bus for 60-degree interval, and the same phase as phase R is clamped to negative DC bus for equal interval of time. That's what I have written. Same is the case with phase leg B and phase leg Y. Clamping of each phase to a DC bus takes place over certain intervals in a line cycle. So that is about continuous and discontinuous PWM techniques, and among these discontinuous PWM techniques, one of the techniques that we discussed in one of the classes a couple of lectures back was continual clamp PWM technique. That is 60-degree clamp PWM technique. This was discussed by us in details, and I tried to explain it with the help of waveforms also. So one of the waveform was something like this. If you remember, this is omega t axis. Let me take one phase. Bus clamping was achieved like this. Okay, so this is phase leg R, say for example R phase. It was clamped from 60 degrees to 120 degrees to positive DC bus for positive half cycle, and in negative half cycle from 180 plus 60, that is 240 degrees to 300 degrees to negative DC bus in the negative half cycle. Another variation of this 60-degree clamp was like this, if you remember. It was like this. Clamping was done in the first quarter. Similarly, clamping was done here. Okay. Here, clamping was done before 90 degrees. For example, it was done from 30 degrees, but this could be 90 degrees. 30 degrees to 90 degrees in first quarter of this half cycle. And then in the negative half cycle, it was done from 210 degrees to 270 degrees in the first quarter of this half cycle. Another variation which was discussed by us, if you remember, was like this. Clamping was done from 90 degree onwards. For example, clamping was done from 90 degrees to 90 plus 6 is 150 degrees in positive half cycle, and in the negative half cycle 270 degrees to 270 plus 60 is 330 degrees. That is in the second quarter of the half cycle. So these are the three variations of 60-degree clamp PWM or continual clamp PWM. In the first case, the clamping of a particular phase was done in the middle of the half cycle, say from 60 degree to 120 degree in the positive half cycle and 240 to 300 degree in the negative half cycle. I told you that this is suitable for those loads which are operating at near unity power factor, because at near unity power factor the current IR, for example, will have maximum value from this interval to this interval, and it is better to clamp a particular phase leg to positive DC bus or to negative DC bus in order to reduce the switching power losses. The rule is that when current is going through its maximum value, at that moment or during that interval itself, bus clamping should be done. That will reduce the switching power losses significantly. For leading power factor load, the 60-degree clamp is shifted in the first quarter. Like clamping is done from 30 degrees to 90 degrees in positive half cycle and 220 to 270 degrees in the negative half cycle. That is in the left quarter or first quarter of half cycle, not in the middle. Okay, because for leading power factor loads, the current is going through maximum value during this first quarter in positive half cycle as well as in negative half cycle, and we clamp the phase, that particular phase, to positive DC bus or negative DC bus at those during those intervals. And this is suitable for lagging power factor loads. Lagging power factor loads. For lagging power factor loads, I told you that current is going through maximum value, say for example in the positive half cycle in a particular phase during this period, 90 to 150 degree. And in the negative half cycle, it is going through the negative maximum value from 270 degrees to 330 degrees. So we clamp a particular phase leg to positive DC bus and to negative DC bus during that intervals itself. That's in the second quarter of half cycle. So therefore 60 degree clamp with the clamping done in the middle of half cycles, it's suitable for unity power factor load. If clamping is done for 60 degrees in the first quarter of half cycle, like in this case, it's suitable for leading power factor loads. And if the clamping is done in the second quarter of half cycle, it's suitable for lagging power factor loads. This we have already discussed in details. And then in previous class, that means last class, we discussed about split clamp PWM technique. Split clamp PWM technique. And in split clamp PWM technique, we discussed like 30 degree clamp PWM technique. We discussed 45 degree dash 15 degree, 45 dash 15 degree clamp PWM technique. And we also discussed, in fact, I gave you an assignment to draw the waveforms for 50 dash 45 degree clamp PWM technique. Okay, for example, 30 degree clamp is something like this. In first 30 degrees clamping is done, then in next 30 degrees clamping is done, say for phase leg R. Instead of doing clamping for 60 degrees continuously, we split it into two intervals. In the first quarter of waveform, half wave cycle, we do the clamping for 30 degrees, say for 30 degrees to 60 degrees. In the next quarter, we do the clamping from, say, 120 degrees to 150 degrees. So this is split clamp. Or we may do in the first quarter for 45 degrees, in the next quarter for only 15 degrees. Or in the first quarter for 15 degrees, in the next quarter for 45 degrees. It depends upon the power factor load. And I told you that this split clamp PWM technique is suitable for very low power factor loads. Very low power factor loads. Like say if you are using inverter for your D-STATCOM application for reactive power compensation, or for STATCOM applications where power factor is very close to 0. There we go for split clamp PWM technique. And the advantage of split clamp PWM technique over continual clamp PWM technique is that it gives better harmonic spectrum. Better harmonic spectrum. How it gives better harmonic spectrum than continual clamp PWM technique, that we will study while discussing space vector pulse width modulation technique. There we will discuss this split clamp PWM technique along with continual clamp PWM technique again, and we will prove that split clamp PWM technique is better than continual clamp PWM technique as far as harmonic spectrum or harmonic performance of inverter is concerned. Okay. And in general, for continual clamp PWM technique, that is 60 degree clamp PWM technique, the clamping is done from 60 degrees minus gamma to 120 degrees plus gamma. Okay, where gamma is varies from 30 degrees minus 30 degrees to plus 30 degrees. Let us take example. For gamma equal to 0 degree, So clamping period is, bus clamping period is, or bus clamping interval is, put gamma equal to 0 here. So it is 60 degrees to 120 degrees, and we have already discussed it. Say for phase leg R phase. Let us take gamma equal to minus 30 degrees. If we take gamma equal to minus 30 degrees, okay, or gamma equal to plus 30 degrees, then bus clamping period is, or bus clamping interval will vary from, so gamma take 30 degrees, so 60 minus gamma, 60 minus 30 is 30 degrees, to 120 minus 30 is 90 degrees. This is another variation of continual clamp. I have already discussed you a few moments back. And if you take gamma equal to minus 30 degrees, for example, the bus clamping interval will be, bus clamping interval is 60 minus gamma, 60 minus minus 30, that is 60 plus 30, that is 90 degrees, to 120 minus 30 is how much? Is it 120 degree plus 30? For gamma equal to minus 30, yeah. For gamma equal to 30, it should be 60 plus gamma, sorry, it's not 60 minus gamma. For gamma equal to 30 degrees, it is from 60 plus 30 is 90 degrees, to 120 plus 30 is 150 degrees. For gamma equal to minus 30 degrees, now bus clamping interval is 60 minus 30 is 30 degrees, to 120 minus 30 is 90 degrees. So it has to be 60 plus gamma, not 60 minus gamma. Please correct it. I repeat it. For gamma equal to 0 degree, bus clamping interval is, gamma is 0, 60 to 120 degrees. So in the middle. For gamma equal to plus 30 degrees, the bus clamping interval is 60 plus 30, 30 to 120 plus 30 is 150. So 60 plus 30 is 90 to 150 degrees. That's second quarter. And for gamma equal to minus 30 degrees, it is 60 minus 30 is 30, 120 minus 30 is 90. So bus clamping interval is 30 to 90 degrees, that's left quarter. Okay, in the first case, gamma equal to 0, bus clamping is from 60 to 120 degrees, it is suitable for unity power factor load. For gamma equal to 30 degrees, bus clamping interval is 90 to 150 degrees, it is suitable for lagging power factor load. And for gamma equal to minus 30 degrees, the bus clamping interval is 30 to 90 degrees, which is suitable for leading power factor load. Okay, so this is how to find the clamping intervals. And for split clamp PWM technique, for split clamp PWM technique, how do you find intervals? So bus clamping intervals are, I will write here, bus clamping intervals are like this: 30 degrees to 30 degrees plus gamma, and 90 degrees plus gamma to 150 degrees. Let us take example. Let us take gamma equal to 30 degrees. So therefore, bus clamping interval will be, I will write here, for gamma equal to 30 degrees, what will be bus clamping interval? In the first quarter, this is first quarter of half wave cycle, and this is second quarter of half wave cycle. I mean, if this is your half wave cycle, this is 90 degrees, this is the first quarter, and this is the second quarter. So bus clamping intervals are, let us take first quarter, 30 to 30 degrees to 30 degrees plus gamma. Gamma is 30, 30 plus 30 is 60 degrees. That means from here, 30 degrees to 60 degrees. Bus clamping will be done in the first quarter. So this is first quarter, Q. And in the second quarter, it will be 90 plus gamma. 90 plus gamma is 90 plus 30. That is 120 degrees to 150 degrees. 90 plus gamma degrees to 150 is 120 to 150 degrees. Second quarter, that is 120 to 150 degrees somewhere here. तो ये 30 degree clamp आपको देगा. Okay, and if gamma is 45 degrees, for example, for gamma equal to 45 degrees, bus clamping intervals are like this. Bus clamping intervals. Let us take first quarter. First quarter में 30 degrees to 30 plus gamma. How much is gamma? 45. 30 plus 45 is 75 degrees. और second quarter में 90 plus gamma to 150. 90 plus gamma, 90 plus 45 is 135 degrees to 150 degrees. So it is something like this. पहले quarter में 30 to 75 degrees for a longer period. और दूसरे quarter में 135 to 150 degrees. छोटा clamp. This is 45 degree clamp. This is 15 degree clamp. Okay. So this is for gamma equal to 45 degrees. और अगर gamma आप 15 degrees लेंगे, for gamma equal to 15 degrees, first quarter में clamping interval देखिए. Clamping interval, bus clamping, I will write here bus clamping intervals in the two quarters of half wave are, पहले quarter में देखिए 30 degrees to 30 degrees plus gamma, gamma is 15, 30 plus 15 is 45 degrees. और second quarter में it is 90 plus gamma, 90 plus gamma is 90 plus 15, that is 105 degrees to 150 degrees. So it will be like this. पहले क्वार्टर में 30 to 45 degrees, छोटा क्लैंप 15 डिग्री का क्लैंप. दूसरे क्वार्टर में 105 to 115 degrees, 105 to 150 degrees, longer clamp, 15 degree clamp here and 45 degree clamp here. Okay, that's it. And that is how to find these clamping intervals. And in the end, I would like to share with you some very important points about what should be the features of common mode signal. When you derive the common mode signal, whether this common mode voltage or common mode signal is for third harmonic injection PWM, which is a continuous PWM technique, or it is for bus clamping PWM techniques, which are discontinuous PWM techniques, it must fulfill certain features. Number one, it must fulfill certain requirements. Number one, this common mode signal or common mode voltage, MCM, must have a periodicity of 120 degrees. जैसे for example third harmonic injection PWM में, this was your common mode signal MCM. Doesn't it have a periodicity of 120 degrees? ये देखिए, this is your original modulating wave MR. उसमें आप common mode signal add करते हैं. This is one cycle of original modulating wave. One cycle means 360 degrees. तो ये कितना है? ये इसका एक साइकिल है 120 डिग्री का 120 डिग्रीज, दूसरा साइकिल 120 डिग्रीज, तीसरा साइकिल भी 120 डिग्रीज. टोटल इज 120 degrees plus 120 degrees plus 120 degrees, that is 360 degrees. So it has a periodicity of 120 degrees. या जो बस क्लैंपिंग आपने स्टडी किया लास्ट क्लास में, उसमें ऐसे था. वन टू थ्री यह आपकी कॉमन मोड सिग्नल फॉर एग्जांपल थी. ये आपकी मेन एमआर थी और उसमें आपने इस टाइप की कॉमन मोड सिग्नल ऐड की. यहाँ से यहाँ तक 360 डिग्री है. ये कितने साइकिल्स है? 1, 2 and 3. सो दिस हैज़ periodicity of 120 degrees plus 120 degrees plus 1. This has also a periodicity of 120 degrees. So MCM must have a periodicity of 120 degrees. And when it has a periodicity of 120 degrees, that means for one cycle of original modulating wave, the common mode signal must complete 3 cycles. So therefore, it must have only triplet harmonics. MCM must have triplet harmonics also, only triplet harmonics. Triplet harmonics means third harmonic and multiples of third. 3, 9, 15, 21 and so on. 6 भी 3 का multiple है, 12 भी 3 का multiple है. ये these are not there in the MCM, because MCM ऐसे है, MCM is like this, or it is like this. So since it has a half wave symmetry, this MCM or this MCM has half wave symmetry, because of half wave symmetry even harmonics उसमें नहीं होंगे. So because of HWS, that is half wave symmetry, even harmonics are not present. Even harmonics are not present in common mode signal MCM. That's 6th, 12th, etc. They are not, only odd harmonics and third harmonic and multiples of third, that is triplet harmonics are present there. And since the waveform has a periodicity of 120 degrees, it has a frequency of 3 times the fundamental frequency, so obviously it will have all triplet harmonics, 3rd, 9th, 15th, 21st, and so on. And finally, last requirement, which is very important, is that for uniform or equal loading of all the 6 devices of inverter, 6 devices, 6 IGBTs of inverter, every MCM, that is the common mode signal, must have 0 average value, 0 average value. और वो क्लियर भी है, ये आपकी MCM है. So what is this? It's AC in nature, alternating. What is its average value? 0 average value. या अगर आपकी MCM ऐसे है, which we have discussed in continual clamp PWM or 60 degree clamp PWM, आपकी MCM ऐसी है. What is its average value? Its average value is 0. The question is, if average value is not 0, then what will happen? So for example, आपकी MCM ऐसे होती है, ये आपकी ओरिजिनल मॉड्यूलेटिंग वेव है और आपकी MCM ऐसे होती है, या आपकी MCM ऐसे होती है नीचे से. This has a positive average value and this has a negative average value. If your MCM would have been like this, with a finite positive average value, then it would have caused bus clamping of only bottom devices. Only bottom devices would have been on, would be on. Top devices की switching होती रहती. That means your phase legs or Y and B would have got clamped to negative DC bus, not positive DC bus. On the other hand, अगर आपकी ये what we call as common mode signal ऐसे होती, नीचे की तरफ होती, this would have caused only top devices to conduct, only top devices would be on. That means आपकी तीनों phase legs R by B would have been clamped to positive DC bus only, not negative DC bus. With this type of common mode signal, only bottom devices would have been on for maybe 120 degrees, and with this type of common mode signal, which has also an average value, negative average value, not 0 average value, only top devices would have conducted और bottom devices की switching होती, and that would have resulted in unequal distribution or unequal loading of the devices. In order that equal loading of the devices is there, our common mode signal should be neither of this type nor of this type, but it should be something like this. Yeah, something like this. I mean, should have positive half and it should have negative half also, like this. Should be something like ऐसे और ऐसे और ऐसे. Positive half इसका और negative half इसका, and then positive ये positive half और अगले वाले का negative half. That is what we are doing. For example, in continual 60 degree clamp PWM, आपकी common mode signal कैसे है? Your common mode signal is like this. So it is positive as well as negative. And what is its average value? Its average value is 0. Average value is equal to 0. So this will cause, clamping of your inverter phase legs to positive DC bus, and this would cause clamping of inverter phase leg to negative DC bus. So that means top devices are on, bottom devices are also on. And you have seen that all the 6 switches, S1, S2, S3, S4, S5, S6 of the inverter, they are on for 60-degree interval each. This is on for 60-degree interval. This is also on for 60-degree. All switches are, so therefore there is equal loading of all the 6 switches. So this is possible only if common mode signal is AC in nature. It has 0 average value. Otherwise, if your common mode signal is like this, then it will result in unequal loading of the devices. Only top devices will be conducting, bottom will not be conducting, or only bottom devices will be conducting, top will not be conducting. So therefore, your common mode signal should be something like this. It should not be like this, or it should not be like this only. It should have positive peaks, negative peaks also. It should be positive as well as negative, so that its average value is 0. When its average value is 0, it will cause clamping of your inverter phase legs to positive DC bus as well as for negative DC bus for equal intervals of time, and that will cause conduction of all the 6 switches of the inverter for equal interval of time, say for 60-degree each. It will result in equal loading of the devices. So these are some of the features of common mode signal. Number 1, common mode signal must have a periodicity of 120 degrees. So therefore it will have only triplet frequencies. And another thing is that the common mode signal must have 0 average value for equal loading of all the 6 devices of inverter. So that was summary of what we have discussed in module number 3, especially in 3-phase PWM voltage source inverters, continuous PWM techniques like sine triangle modulation or third harmonic injection PWM technique, and discontinuous PWM techniques like various bus clamping PWM techniques, and features of common mode signal and all that. With this, I will end my today's lecture, and I am pleased to announce that this marks the end of module 3. Your syllabus of PWM techniques comprises of 4 modules, and we have already completed 3 modules. Today we have ended module number 3. Inshallah, from our next lecture we will start module number 4, and module number 4 is mostly in module number 4 we'll be mostly discussing space vector pulse width modulation, SVPWM techniques. I request all of you, I advise all of you to go through all these lectures, study all the 3 modules which we have covered till now, module 1, module 2, module 3. Study them, revise them. In case of any doubts, put your doubts, your queries on the WhatsApp group, or you can personally message me about your doubts. I'll be pleased to clear your doubts, to reply your queries. So please go through all these lectures. Thank you.